Hey guys, hope you're doing well. Slim is not the best stock person, I have to tell you. It's hard getting good help sometimes. So he put this weak acid inside this flask, but didn't label it. I know it's a weak acid, I know it's acetic acid, but he didn't label what the concentration was. Come on, Slim. Anyway, there is a way I can figure this out, and we're going to do this together today. This is called a titration, and it'll show you how we can determine the concentration of an unknown based on using the concentration of a known. Let's go. The concept behind a titration is what we call a neutralization reaction, where you have an acid and a base, and when they combine to give us a salt and water. So because of this, I'm going to use a known solution. I've got 0.1 molar NaOH in this flask right here, and I'm going to use it and see how much of this volume I need to neutralize the acid that I have. And I'm going to use a known quantity of the acid. In fact, I'm only going to use about 5 milliliters of the acid. Now I'm putting this known volume into my beaker. I'm going to have a certain amount of moles of acetic acid in that beaker. You get that? I'm going to put some distilled water in with this so that I can actually see the volume a little easier. 5 milliliters isn't a whole lot to see when it comes to a beaker like this. Now if you're wondering about the concentration, it's okay. Here's why. I know exactly how much volume I put in. Remember, molarity is in moles per liter. So I know exactly how much volume I put in, and the moles aren't going anywhere. I'll have the same amount of moles in there regardless of how much water I put into it. Does that make sense? So once I understand how much I needed to neutralize this acid, then I can use that information and come up with a molarity. I think you'll see what I mean in just a moment. I'm just going to pour a little bit of this distilled water in here just so I can see it a lot more clearly. Now this is called a burette, and you'll notice it has numbers on it. It's graduated, like a graduated cylinder. And these graduations are pretty precise. I can use this to know exactly how much volume that I start with and I end with. In other words, how much volume of this NaOH I'm going to use to neutralize this acid. I'm going to make sure that this valve is closed. It needs to be crossways and not this way, otherwise it's going to start pouring into my beaker. So I'm going to make sure it's closed, and I'm going to pour, using a funnel, I'm going to pour some NaOH into my burette. Now one thing I do after I pour my known solution into my burette is that I'm going to open it so that I have no bubbles, because I want to know exactly how much volume I'm using. So if I don't have anything in this little nozzle here, that's going to give me a false volume. So let me go ahead and open this just a little bit, and I can just get rid of this, put this off to the side. Now that I've gotten my nozzle free from any bubbles, I'm going to top this off a little bit more so that I have plenty to use. I'm going to show you where my volume is at this point, and you can see it's really close to 1 milliliter. I'm going to say that this is 0.96 milliliters. Oh, by the way, you may have noticed this, but I want to make sure to point it out. These numbers go from 0 to 50 and not 0 to 50. That's because since I'm releasing the solution, it's going to be moving this way, isn't it? So I want to be able to count upwards and not backwards. Now before I start, I'm going to put a few drops of this into it. You might be asking what this is. This is an indicator, an acid-base indicator. It will change color depending on the amount of hydrogen ions or hydroxide ions in the solution. Pretty cool, huh? This one's called phenolphthalein, and it starts out as being clear, and it will stay clear as long as you have an acidic environment. So if I place a few drops in this weak acid, it will still remain colorless. But when phenolphthalein is exposed to a basic environment, it changes color. I don't want to give it away. It's pretty cool though. All right? So the idea here is once we cross over into basic land from acidic land, that's going to change color for us. I can stop adding NaOH at that point, and I can figure out exactly how much volume I've used, and then determine the molarity of this unknown acid. You ready? Hey, this is pretty cool. This is my magnetic stirrer. So when I turn this on, there's this little magnetic bar in there. You can see it spinning, and as it spins, it allows it to be mixed very well. I don't have to sit and shake the beaker or stir it or anything like that. If you want to get really, really precise, you can use one of these. This is a pH meter. And when you leave this pH meter submerged while you're doing the titration, you can add a little bit and then take down a reading. Add a little bit more and take down a reading. And from it, you can get an actual graph of the titration. Now, in just a moment, I'll show you what a graph looks like for a titration. And you can see exactly where the crossover happens from an acidic pH to a basic pH. So here we go. There's a tiniest little bit of a color that as these drops of the base are added in, you can see it. And I'm also looking at my pH meter, and I can see my pH meter increasing in pH, which means I'm going more and more toward the basic zone of pH. You see that little bit of color happening there? What we want is for that color to stay. We know that when the color stays, that we've hit the point that we need to. Getting really close. You can see how it's staying a little longer. Oh boy. Can you see it? That's what we want. That's what we want right there. We want it to be the slightest bit of pink. Pink is the color that we see when phenolphthalein moves into a basic environment. So it's starting to go away just a little bit. I'm going to add one more drop. One little drop. You see a little bit more now? That's a pretty good place. I'm going to take that reading. I'm going to take the reading where I am as far as my volume is concerned, and I'm going to call that my volume. But then, you know what? I'm going to add a little more so you can see the pink color a little better, okay? But first, 43.30. So I'll write that down. So I've got my volume. Now I'll let you see the pink a little bit more. I'll go ahead and just drain this out. That's a cool color, isn't it? Really pretty. A pretty magenta, pinkish color. That's how we know where to end. A few terms that you should know. First of all, we have a special term we use for this known substance that we use in our burette. It's called the titrant. The titrant. Again, a known volume of the titrant is used to neutralize a known volume of the acid. Now, in the case of the titrant, we actually know what the concentration is. So having that concentration and a volume, we can compare moles of titrant to moles of the acid in this case. Acetic acid is monoprotic. It only has one hydrogen to offer as an acid. NaOH has one OH to give. So this is a one-to-one neutralization situation. And that's good for us in calculation purposes. So now I'm going to take us to the whiteboard so we can do some calculations and to show you what the graph looks like of a titration. Let's explain again what's going on in a titration. It's based on the principle of a neutralization reaction, where we have an acid and a base that combine to give us a salt and water, thus neutralizing both. Now, if we had something along the lines of a strong acid and strong base situation, this is what our titration graph would look like. Let's say we were titrating a strong acid like HCl with a strong base like NaOH. Let's say that we have 30 milliliters of 0.1 molar HCl and we're titrating with 0.1 molar NaOH. Here is what we would see from our graph. The NaOH would be the titrant, the solution we put in our burette. If we were measuring the pH inside the beaker, we would see at the beginning a very strong acidic pH. But as we add the titrant, the NaOH, notice that the pH begins to increase slowly but surely until finally it gets to this point right here, notice around 30 milliliters, and all of a sudden it skyrockets into the basic zone, and then it begins to level off again. So what's going on? Why the skyrocket? Well, think of it as sort of like a balance between hydrogen ions and OH ions. As long as we have one more hydrogen ion than we do hydroxide ion, that solution will be in the acidic realm. right? But the moment that we have one hydroxide ion higher than the hydrogen ions, we go up into the basic zone. So we see this extremely high slope right here because we are changing from the acidic realm to the basic realm. We're looking for the point at which our hydrogen ions equal our hydroxide ions. We call this the equivalence point. And that's the point that we see here right around pH of 7. In a strong acid, strong base situation, we do see the equivalence point right around the neutral zone, pH of 7. Now let's be honest for a second. We're probably not so good that we can find the exact point at which the hydrogen ions equal the hydroxide ions. Remember, there's like a gazillion of each in one drop of that solution. So because of it, we look for something else. We look for the point at which the color changes, that our indicator color changes in that solution, and that's the point that we call the end point. That's what we're looking for to know when to stop titrating. So just to recap, the equivalence point is the actual point in which hydrogen ions equal hydroxide ions, but the end point is the point where we see the color change. That's the point at which we actually end the titration. But you know what? We don't always find our equivalence point hits right at pH 7. In this case, we have a weak acid, acetic acid, being neutralized by a strong base, NaOH, to give us sodium acetate, a salt, and water. Now, notice that our equivalence point is up here around the 8.5 range. It's still the area in which we see equal amounts of hydrogen ion and hydroxide ion. But why does it shift upward a little bit? That's because of something we'll see in our next video. Because the strong base reacting with that weak acid produces a salt that's actually basic itself. With this basic salt still being around, it tends to turn the tables in the direction of the basic realm. I think you'll understand what I mean after our next video. Nonetheless, we can still see this classic titration curve, can't we? Where we see the acid realm and we increase slowly until we get to this point right here, and that's the point at which it goes up and into the basic realm. We can still see approximately where the equivalence point is. Our end point, in the case of the titration we did earlier, gave us that nice pink coloration to know it was time to stop. So with the information we've gathered, we can figure out what the concentration is of this acetic acid. We used 42.34 milliliters of 0.1 molar NaOH, and we titrated 5 milliliters of this unknown solution. So let me show you how to figure out what the concentration of that solution is. We're going to figure out first how many moles of NaOH we actually used. Why? Well, because remember, it's a 1-to-1 situation. For every mole of NaOH, we are neutralizing 1 mole of acetic acid. So we can know how many moles of acetic acid we neutralized if we find the number of moles of NaOH we used. Get it? We have 42.34 milliliters. We need to convert that to liters. Why? Because remember, molarity is found in moles per liter. We convert to liters by saying that 1 liter equals 1,000 milliliters. In doing so, we see that milliliters cancels, and that gives us liters of NaOH. Next, we convert to moles by multiplying by the molarity, 0.1 moles per liter. Notice that the liters units cancels, and we're left with moles of NaOH, just like we want. So when we take 42.34, divide it by 1,000, and multiply by 0.1, we get 0.004234 moles of NaOH. Remember, that's going to be the same amount of moles of acetic acid. So for every 1 mole of acetic acid, we need 1 mole of sodium hydroxide. Notice that this neutralization reaction is a double replacement reaction. We're simply trading partners, aren't we? The hydrogen pairs with the hydroxide and gives us water. The acetate ion pairs with the sodium and gives us the salt, sodium acetate. So since it's a 1-to-1, we know that we had 0.004234 moles of acetic acid And remember, we used 5 milliliters. Got to convert that. So 5 divided by 1,000 gives us 0.005 liters of acetic acid. You do the math, and we come up with a molarity of 0.85 molar acetic acid. Your mustache is kind of, yeah, there we go. So I hope you're happy. You know, these nice people had to come to your aid and figure out the concentration, all because you're a little too lazy to label properly. Okay, I hope we've learned a lesson from this. Okay, all right. It's important to note that certain indicators are better used for certain situations. For instance, I knew that I had a weak acid and I was titrating with a strong base. So I knew my equivalence point was probably going to be up around this range. That happens to be the perfect range for phenolphthalein. That's where its color change takes place. So that's the one I picked. For other situations, I would use an indicator that best suits the equivalence point for that particular titration. And we've got all kinds of indicators we can use. So that's all the time we have for this video. We started by doing a titration together and showing the actual techniques involved, and then we showed how we can make a titration graph based on the information from that titration. We talked about neutralization reactions, how you have an acid and a base that combine to give us a salt and water. We also talked about 2 points that are very important to us in the titration. One, the equivalence point, where the hydrogen ions equal the hydroxide ions, and the other point was the end point, the point at which we see an actual color change take place, telling us that we can stop titrating. And last but not least, we showed how we can take the information from our titration and use it to come up with the actual concentration of an unknown. I hope this is informative for you. I hope you enjoyed watching the titration. And as always, if I can be of help to you, please let me know. Until the next time, God bless.